paracyclic reactions, the Cope and Claisen rearrangements. So let's see what's going on. Okay, here's phenol. We're going to do an interesting experiment. We're going to make the anion, the phenoxide, and then we're going to react it with the allyl bromide. So what do we expect? Well, the phenoxide can do an SN2 substitution, very straightforward. Or you can imagine doing a completely different reaction where we treat the phenoxide as an enolate, because I mean there's a double bond down here, and we could form the carbonyl. The double bond could reach over and do the SN2 type reaction. Then we'd end up with this strange looking keto compound here, which of course would tautomerize back to the phenol. Well, that looks pretty weird, but what does really happen? Well, of course the first reaction happens. A is the one that we get. So we have this guy. But the interesting thing is, if you heat this up to 200 degrees, we get the product from reaction B. So what in the world is going on? Well, it's a paracyclic reaction. And to understand this, what we have to do is simply look at the mechanism. So the first thing we want to do is redraw the starting material here in this new conformation. And now what we're going to do is simply look at the cyclic flow of 6 electrons, 3 arrows. And so what's happening here? Well, you can look at essentially the think of this I guess now as your double bond, your ring out here reaches out, forms a new double bond at the end of the allyl, push the double bond up here, we break the CO bond, forming the carbonyl. And here is that same product that we had on the previous slide, which is this ketone, which will tautomerize back to the phenol. So this is a very strange looking reaction, and but it's a member of a family of a much larger set of reactions. This is called the Claisen rearrangement, and it's the same Claisen as the Claisen condensation, but a completely different reaction. Now this is a paracyclic reaction, cyclic flow of 6 electrons. It's a concerted reaction in the sense of this thought that all these things happen at the same time. As you form this double bond as the same time, they form this bond as the same time as you're breaking that one, and the double bonds are moving. So everything happens at once. Now, the fun thing here is that what if you had this isotopically labeled? What if we had a carbon-13 out here at the end? Which of these would we get? Well, you look through the mechanism. Where does the carbon-13 go? So we would say, well, here's our carbon-13 at 200 degrees. This is going to be originally on the end here, but when you form the new bond, of course, that's the one that's going to attach to the carbon. So originally it was away, now it's attached. So it's easy to track down what's going on mechanistically by the carbon-13 label. So this is the Claisen rearrangement. Now, this is a review of the Diels-Alder. The Diels-Alder we thought of as a 4+2. We had our butadiene, we had our dienophile, our alkene, and we had these nice homo-lumo interactions. Can we do a same thing for the Claisen? So here, again, this is 4+2. The Cope rearrangement you could think of as in kind of a weird way as a 3+3. But it's a little bit strange because this is really just a thought experiment. Don't think about what this really happens. There's really no real radicals. But imagine that we had 2 radical anions sitting here in space. Now we don't have these. We start on the left-hand side with a chemical bond. But imagine just breaking this bond as a radical on each side. We'd form these 2 allo groups apart from each other, and then we just join them back on the other side. And what you would think of in MO terms is that you'd have an allo fragment here with a single electron, of course, doing a perfectly match with the allo on the other side of a single electron. And so this is a great interaction, and it's obvious that this could just go back and forth. And if A or B happen to be more stable, the equilibrium would favor A or B. If they were of equal stability, then in principle it could just keep going back and forth. But if you don't like that thought experiment, think of it as an anion and a cation. Again, this is a thought experiment. There's no real charges. But think of an allyl anion and an allyl cation. And so now what we're going to do, we're going to set this up as essentially as a 2+4 interaction again. Because here I've got only 2 electrons, so this is the cation. This has got 4 electrons, so this is now the anion. Again, this is only a formalism. There are no real charges. We're just doing this as a mental exercise. But again, now you'd see that the highest occupied orbital here would match perfectly the lowest unoccupied orbital. In this case, this would be the, since these are both in the middle, this would be the important interaction. So again, what you can think of is that you break this, you assign both electrons to this bond, so that's a cation, and then you reform it over here. Now this isn't what really happens. It's a concerted reaction where you never really have these intermediates because the bond is broken, the new bond is made at the same time in a concerted manner. But it helps it kind of an MO picture, give you an MO picture of what's going on. Okay, so that's the Cope reaction. But there's another one. I'm sorry, that's the one we talked about was the Claisen. The one with all carbon is called the Cope. I guess I wasn't clear on that. Claisen has an oxygen in it. Cope is all carbon, but the reactions are essentially identical. The Claisen often has an extra driving force because you can get this carbonyl compound, and carbonyls tend to be a carbonyl is more stable relative to a carbon-oxygen single bond than a carbon-carbon double bond is relative to a carbon-carbon single bond. So usually when you form that carbonyl, you have a driving force for the reaction in the Claisen, which you don't necessarily have in the Cope. And of course, the other kind of paracyclic reaction was the decarboxylation, which we've been doing for quite some time, or the other examples of enes, which we talked about earlier. Okay, so how do you recognize a Cope reaction? Well, the key thing is it has to be two double bonds, and if you number these bonds, they have to be 1 bond, 2 bonds, 3 bonds, 4 bonds, 5 bonds. You have to have a 1,5 diene, okay? And you redraw it as it was a 6-membered ring with a gap, and then you just basically switch the bonds around. And so it's pretty easy to see what the product is once you get it in this proper redrawn configuration. That's the key thing on doing and figuring out these Copes is redraw it, and then it's easy to shift the bonds. You just do the set of cyclic arrows, and you rapidly go from one to the other. And of course, you can go back. And which one you actually get depends upon which one is thermodynamically more stable. So in this case, you want which one's going to be more stable. Well, if you look at this one has 1 double bond in conjugation of the phenyl, so there would be a driving force to go to the right simply because of that added conjugation. And more substituted. These are both terminal alkenes. This we get a disubstituted one and conjugated to the phenyl, so it's going to go to the right. So let's do one of these. This is obviously a 1,5 diene. I've got it already labeled. It's already laid out. So can you write down the product? And I'll give you some choices. But now, what do you want to do? Just draw the arrows and do it. So pause the video a little bit. Figure out what this is. Okay, you got it figured out. So what do? We just redraw. Okay, even better. All right, and then I do my Cope, and so this bond breaks. New double bonds here. New single bonds here. New bond there. It's this guy right here. And which one is that? Aha! Very good. It's E. Very good. You figured that out. Okay, do it again. So again, see if you can figure this one out before I'm going to give you some choices, but again, stop the video, see if you can figure this one out. So again, this is a 1,5. If you look, it's a 1,5 diene. 1, 2, 3, 4, 5. Redraw this piece and then move the bonds. So predict the product. Okay, so redraw. Okay, that's what you're supposed to look at, of course, but you got to put on the substituents. So here's some choices. Which is it going to be? Which is it going to be? Got it figured out? Okay, so there's the redrawn product. All right, and there's the Cope reaction. So which one is it down here? We got a cis interaction here, and then it looks like B to me. Okay, so very good. Hope you got that right. Okay, let's do a final example, which is really weird, I warn you. So can you do the Cope on this guy? Now this looks a little bit strange, but again, it's 1, 2, 3, 4. Okay, so I'm sorry, I'm going the wrong way. 1, 2, 3, 4, 5, going around to the left. And so what's going to break? Well, we're going to break this bond. The double bond's going to move here, and we're going to form a new bond across there. So can you draw out the product? Okay, what's the product? Well, of course, if you do the arrows, what do you get? Well, you get the same molecule pointing the other direction. It's A. So that's pretty bizarre. So this molecule it's symmetric in the sense of it doesn't cope, it just interconverts two forms. So if it started off with a carbon 13 at the apex of the three-membered ring, that would end up as the bottom of the seven-membered ring. That's pretty weird. But let's make it more interesting. So if you think about this, this is two ends of the cyclopropane ring joined together by these bridges. Here's the third point up here. Let's join it by a same bridge. So now all these bridges are the same, right? So this is now a molecule with threefold symmetry. It's got carbon of 3 bonds on top, and it's got a cyclopropane on the bottom. And this atom is each joined to a vertex of the cyclopropane by this essentially I guess you call it vinyl bridge. So this is a nice symmetrical molecule, and it can redraw it this way. You can see the threefold symmetry a little bit better. Well, this molecule is really bizarre. It's called Bolvoline, which has to be one of the neatest names in all of chemistry, Bolvoline. But and here's just a bunch of pictures of Bolvoline showing you different views. It's got threefold axis down the middle. Now the fun thing is that this thing can still do Cope reactions. But now if you look at this, it can do them all over the place, because any side of that molecule, and you can break any one of those 3 bonds on the cyclopropane ring and do a Cope, and each time you do it, you'll get a new bond down below, which does the same thing. So here I've broken this bond, I form a new cyclopropane down there, and I've got the same compound back again. So again, it goes to the same compound, and you can simply keep going. So this is a really famous molecule. There's a nice article in Journal of Chemical Education that discusses this. You might want to look it up. You also can find it on Wikipedia. But if you number the atoms and you look through the series of Copes, what you will find that every atom works its way through this structure to occupy every possible position. So look at atom number 8 up here at the vertex where everything comes together. So here it was in the cyclopropane ring. Here it was on the double bond position. Here it's a different. Well, it's double bond. There's back to the vertex. Everything just moving around like crazy on this thing. Every atom ends up one time or another in each of the various possible places. So Bolvoline is a very confused molecule, and this molecule is said to be fluxional in the sense that if you heat it up, all the atoms in the molecule basically change positions. They're constantly interconverting, and that is about as cool as molecules get. So that's the Cope reaction. Now we can also talk about some variations. There's something called the Oxycope. The Oxycope has an oxygen, but the oxygen is not involved in making and breaking the bonds. But what it does do when you do the Cope, it turns the OH becomes part of an enol. And when it comes an enol, of course, enols will tautomerize to, in this case, an aldehyde. And that's the driving force for the reaction, because now it's not going to go backwards, because to go backwards, you'd have to reform the enol, which is unfavorable. So this is the Oxycope. And so the Oxycope here, you just do the Cope, and again, what you're going to do is you're going to get an enol, which you then tautomerize to the ketone. So can you work out the product? Here's some choices. Okay. Look at them. Of course, what's going to happen is we're going to make a new bond here. We're going to break the bond in the middle. So it's going to be one of these ones broken in the middle, and I've already kind of given it away because I said we're going to make a ketone. So there's our enol, and of course it tautomerizes to D. So that's the Oxycope. And the neat thing is that this thing has a trans double bond in it, and that trans double bond you normally don't think of as in a ring, but it's a natural consequence of the fact when you have the starting material, its best conformation is with these two groups equatorial, and they want to form a chair-like structure. So it wants to line up this way, and the new double bond is going to be this one, right here, which is going to be naturally trans. So you can get some strange goings on in these things. So we'll do this one last example and then we'll quit. Can you do a cope on this one? It's an Oxycope. There's our this is going to be our Carbonyl. Now this is really hard to draw. For one thing, it's hard to line these things up, but the first thing to do is simply to count 1, 2, 3, 4, 5. So can you draw the new product? Again, pause the video, see if you can figure this one out. It's going to be a quiz down below. Okay, there's some candidates. You just want to scream, I know. Okay, so how are we going to figure this out? There's the molecule. Look at that. What have I done? What have I done? Well, what I've done is I've drawn a new bond from here up to there. I've shifted this double bond here. This one goes here. That's the bond that's broke. So I just did the transformation. In other words, we can start here, swing over, form the new bond up here, swing this double bond over there, break that double bond, swing it down there. Those are our arrows. And